Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good morning. I hope all of you are doing well. So for today's lecture, we are going to continue with our topic on shaft power cycle. But just to note to you that we are going to have a short break probably right after this first lecture, and we will have our quiz as highlighted last week. We are going to have a quick quiz so that everybody is on the right track. So let me share my screen. I hope you can see the slide in front of you and you can hear me very well. Okay, we have looked into the introduction to air breathing engine last week. I believe some of you managed to look into the YouTube videos that I have uploaded, right? I hope it is useful, right? Probably some of you have no time to look at it at all, but we'll see when you try to answer the quiz for today, right? Okay, with regards to shaft power cycle, this is the second topic on air breathing engine. We will look into several subtopics under this shaft power cycle, and it is the first one is ideal cycles, and then methods of accounting component losses, and we have design point performance calculations, comparative performance of practical cycles, combined cycles and cogeneration schemes, closed cycle gas turbine. Right. So for today, we are going to look into the first one, which is the ideal cycles, which is being divided into ideal cycle, simple gas turbine cycle, heat exchange cycle, reheat cycle, and cycle with reheat and heat exchange. And we will continue after the short break, probably at around 10 a.m. after we have our quiz, and then we will continue on 2.2. In terms of the learning outcome, so at the end of this session, you should be able to describe methods of calculating cycle performance, right? We have looked into what is cycle all about, what is the performance of air breathing engine, right? You should be able to describe the methods, calculating cycle performance, and explain the assumptions of ideal cycle conditions, as well as compare the different gas turbine cycle, heat exchange cycle, reheat cycle, and cycle with reheat and heat exchange. Those are the learning outcomes for today's session. And this is for the first part of today's session. If we look at the ideal cycles, there are a number of possible varieties of gas turbine cycle when multi-stage compression as well as expansion, okay, heat exchange, reheat, and intercooling are incorporated. So you can have a various varieties of possible gas turbine cycle, as we have shown in the introduction last week, where you have looked into a simple gas turbine cycle, open cycle, closed cycle, cycle with heat exchanger, there are intercooling, there are reheat, there are power generators, and so on. And so we can have variable varieties in terms of the type of gas turbine cycle. We cannot run away in terms of the inefficiencies, when we look into the performance of the gas turbine engine, we need to relook at the components efficiencies. So inefficiencies of various components would result in a very large number of performance curves. By having different components, different numbers of heat exchanger, you have intercooling or reheat, or multi-stage compression and expansion, you will generate a different performance curves. And the specific output, a specific work output, as well as the cycle efficiency will depends only on the pressure ratio and maximum cycle temperature. So those are the two items that we need to consider: the pressure ratio, right, and the maximum cycle temperature whenever we want to look into the specific work output as well as the cycle efficiency. Right. In order for us to deal with ideal cycles, there are 6 assumptions that we need to relook and we have to take into consideration. The first one is the compression and expansion processes are reversible as well as adiabatic, right? So we have to take note on that, where we assume, right, the process for compression and expansion are reversible as well as adiabatic, or in other words, it is isentropic, right? And the change of kinetic energy, the KE, I will use KE as kinetic energy throughout the course, of the working fluid between the inlet and outlet for each component is negligible. So this is very important. Okay, so the change of kinetic energy of the fluid between inlet and outlet, let's say from the inlet of the compressor, okay, and the outlet of the compressor, the kinetic energy of the working fluid is negligible. Okay, that is we need to take note on that. And then the number 3, the assumptions that we need to take into consideration: there are no pressure losses, right? We assume no pressure losses in the inlet ducting. Okay, meaning that the pressure remain consistent. There's no losses in the inlet ducting, the combustion chambers, the heat exchangers, intercoolers, exhaust ducting, and ducts connecting the components. So this is to make life easy, the calculation that we need to consider, that there are no pressure losses. Okay, and then the working fluid has the same composition throughout the cycle. Meaning that, what does it mean? Okay, the working fluid, let's say it is air, right? Compressed air coming into the air coming from the surrounding into the system, into the compressor. It has the same composition as the ambient air outside the engine. Okay, and it is has the same composition throughout the cycle, and we assume it is a perfect gas, okay, with constant specific heats, right? So you will see why it is very important that we do this kind of assumptions. Number 5 assumption is that the mass flow of gas is constant throughout the cycle. So the m dot, okay, the m dot, we can consider it as constant. Okay, m dot is constant throughout the cycle from the inlet until the nozzle. Okay, and the heat transfer in a heat exchanger, we assume counterflow heat exchanger is complete. Of course, in a real condition, it is not complete. In terms of the heat transfer in the heat exchanger, normally it is about 80% to 90% of efficiency if you have a very good heat exchanger system. And but we assume everything is complete. So that in conjunction with assumption number 4 and number 5 just now, right? The temperature rise on the cold side is the maximum possible, right? So we want the let's say the amount of heat being transferred is maximum, meaning that the cold side temperature rise is maximum as possible and exactly equal to the temperature drop on the hot side. So you imagine you have two sides, the hot and the cold. The amount of heat being transferred from one, let's say there's two sides. This is hot, okay, and this is cold, right? So the amount of heat transfer, okay, from the hot side to the cold side, the high temperature to the low temperature is the amount of hot temperature drop is equal to the amount of cold side temperature rise. right? So we assume it is complete, right? Assumption number 4 and number 5 imply that the combustion chamber in which fuel is introduced, right, in the combustion chamber itself and burn is considered as being replaced by a heater with an external source. Okay, that is we assume in the ideal cycle. As far as the calculation of performance is concerned, it makes no difference whether it is open or closed cycle. Right? Those are the assumptions, the 6 assumptions that we make whenever we deal with ideal cycle. Right. Let us go into the simple gas turbine cycle. Okay, the ideal cycle for the simple gas turbine is Joule or Brayton cycle. I believe you have seen this before last week as well as during the propulsion subject. This is a simple gas turbine cycle. Remember, in our everything course, we only consider the 3 main components, which is the compressor, the combustion chamber, and the turbine. Okay, so this is the simple gas turbine cycle or Brayton cycle, right? The relevant steady flow of energy equation. Okay, I would like to introduce a few equations here. Probably some of you have seen it in your propulsion subject. Okay, the Q, right? The heat transfer per unit mass flow. Okay, equal to the difference between the specific enthalpy. Okay, plus half times the velocity squared at station 2 minus velocity squared at station 1 plus the specific work power output. So where Q and W are the heat and work transfer per unit mass flow. And applying this to each component, right, for compressor, for combustion chamber, and for the turbine, bearing in mind assumption number 2 for ideal cycle. Okay, remember we had 6 assumptions just now, and we can write down the whole equation for the component. Okay, this is at the compressor. Okay, this is at the combustion chamber, and this is at the turbine. Right. So W12 meaning that from inlet station for combustion chamber. Let us just quickly go back one step, right? Station 1, station 2, station 3, station 4. Okay. So you have compressor inlet, compressor outlet, okay, turbine inlet and turbine outlet, so that you can remember what is it all about. So we can apply to this steady flow energy equation. Okay, steady flow energy equation at the compressor, okay, at the combustion chamber, right? We call it as a combustion chamber, and the turbine. All right, let us move on to the cycle efficiency. Okay, we denoted by zeta, right, equal to the net work output divided by the heat supply, and the heat supplied by the combustion chamber, right? So we have here Cp. Cp is the specific heat at constant pressure. Okay, C, small c and subscript P, right? And the temperature difference between the turbine inlet and the turbine outlet. Okay, and the temperature difference at the compressor outlet to the compressor inlet. So divided by the heat supply. This is the situation where at the combustion chamber, okay, specific heat at constant pressure times the temperature difference at the combustion chamber outlet to the combustion chamber inlet. So making use of the isentropic pressure temperature relation, okay, we can write this expression, the ratio between the temperature at the compressor, okay, which is equal to the gamma to the power of ratio of specific heats. Gamma is the ratio of specific heats. It depends on whether it is air or certain kind of gases. We will determine it when we go into the specific example later on, which is also equal to the temperature temperature ratio between the turbine inlet to the turbine outlet, right? Where R is the pressure ratio, okay, where P2 over P1, which is equal to P3 over P4, okay? And the cycle efficiency is equation can be written here, right? Zeta, which is equal to 1 minus 1 over R to the power of specific heat ratio minus 1 divided by specific heat ratio, okay? Right. The efficiency thus depends on the pressure ratio and the nature of the gas. So it depends. If we look into figure 2.2a over here, it shows the relationship, okay, between the zeta and the R, okay, the pressure ratio and this efficiency when working fluid is air, okay, where gamma equals 1.4, or any monotonic gas such as argon, which is gamma equal to 1.66. So depend on the situation. Let's say it is air, you will use gamma 1.4, right? And we can see here at the pressure ratio of higher pressure ratio, the efficiency is increasing, okay, for both the air as well as the gas, monotonic gas. The specific work output, W, can be considered as a function of the pressure ratio and maximum cycle temperature, T3. T3 is the temperature at the inlet of the turbine. It is the same temperature at the outlet of the combustion chamber. Okay, where we write down the expression for the specific work output, okay, and which can also be expressed as equation 2.2. Okay, we express the term specific work output, okay, in terms of the other components, where T, the small t, this is not time. Time normally we consider as theta. This is the temperature ratio. Okay, R is the pressure ratio. T is the temperature ratio for T3 over T1, and T1 is normally atmospheric temperature. Okay, T1 is the gas or the air incoming air from the atmosphere going into the compressor. So it is therefore convenient to plot the specific work output in non-dimensional form. Okay, normally when we deal with gas turbine analysis, gas turbine cycle analysis, we deal with non-dimensional form, right? The specific work output, okay, we plot it again the pressure ratio, and we can have a different temperature ratio range. Different. Let's say you want a gas turbine engine which has a temperature ratio of 5 or 4, 3, 2, and you can find out what are the specific work output for the engine cycle with respect to the pressure ratio. Okay, and to continue, the value of T3, the inlet turbine temperature, and hence the temperature ratio, depends on the maximum temperature which the highly stressed parts, okay, we have the highly stressed part which is the turbine, can stand for the required working life. We have talked about this in general last week about the different material, different cooling technique on the turbine that is affecting the performance or the temperature that it can withstand. And it is often called the metallurgical limit for the turbine. Right? Early gas turbine values of T, or the temperature ratio, is considered to be between 3.5 to 4, but introduction of air-cooled turbine blades allowed the temperature ratio to be raised between 5 to 6, and you have a more modern technology of producing different different type of material that can withstand high temperature and high stress. Let's continue. At a glance of the TS diagram, temperature entropy diagram, it shows why a constant T temperature ratio curve exhibits a maximum at a certain pressure ratio, where the specific work output is 0 and the pressure ratio equal to 1. And this is where the pressure ratio equal to 1. Okay, the specific work output equal to 0. Okay, for which the compression and expansion processes coincide. Right. Let us now move into the next subtopic on ideal cycle, which is the heat exchange cycle. Earlier we have already looked into ideal cycle, simple gas turbine cycle, and now we want to move into heat exchange cycle. Right. For a heat exchange cycle, the cycle efficiency now becomes this expression, where we have another expression of T5. T5. Let us see where is T5 coming from. With ideal heat exchange, T5 equal to T4, right? This is ideal heat exchange situation. And remember, we assume the heat exchange is complete. So the temperature at the turbine outlet equal to the T5. And on substituting the isentropic pressure temperature relationship, the expression reduces to, later on we're going to look at the expression. Okay, this is the TS diagram where we have a heat exchanger. Okay, just before it goes into the combustion chamber. So from the compressor going into the heat exchanger, okay, this is where we have the T5 and goes to the combustion chamber, and we have the turbine inlet temperature T3, okay, and it goes out from the turbine T4 and come back to the heat exchanger as T6. So the expression can be reduced to equation 2.3, right, which is this one. The efficiency zeta equal to 1 minus the pressure ratio times the specific heat ratio minus 1 divided by specific heat ratio divided by the temperature ratio. So thus, the efficiency is not independent of the maximum cycle temperature. Okay, it is not independent of the maximum cycle temperature, which is T3, and it increases as the temperature ratio increases. Right? For a given value of temperature ratio, the efficiency increases with decrease in pressure ratio and not with increase in pressure ratio as for the simple cycle. So there is the major difference between a simple gas turbine cycle with a gas turbine cycle with heat exchange cycle, with heat exchange. Right. The full line in figure 2.4, okay, this is figure 2.4, efficiency against pressure ratio, right? The full line is this, okay, T5, T4, T3, T2, represent the equation each at constant temperature ratio curve starting at pressure ratio equal to 1, with a value of zeta equal to 1 minus 1 over temperature ratio, or we call it as the Carnot efficiency, right? So the specific work output is unchanged by the addition of a heat exchanger, and the curve of figure 2.2b are still applicable. Okay, just now we show the figure 2.2b to gain improvement in efficiency, right? How are we going to improve the efficiency? By having heat exchange, a value of R, the pressure ratio, should be less than the optimum for maximum specific work output, right? It should be, the pressure ratio should be less than the maximum W, and W is the maximum specific work output, and not necessarily use a higher cycle pressure as the maximum cycle temperature is increased. Later when we deal with example, probably you can see this point clearly, right? Then we'll move into reheat cycle. Just now, heat exchange cycle. Now, what happens if we introduce a reheat cycle? So another combustion chamber into the system. A substantial increase in specific work output, W, can be obtained by splitting the expansion and reheating the gas between the high pressure and low pressure turbine. And it's shown in this figure, right? So you have another peak here, right? Where you burn the uh, gas in another combustion chamber. So show the relevant portion of the reheat cycle on a TS diagram. So the turbine work is increased is obvious. Okay, so of course you reheat the gas twice in the combustion chamber, meaning that the temperature goes much higher, and the vertical distance between any pair of constant pressure line increases as the entropy increases. Thus, right, the temperature T3 minus the difference between the temperature at the turbine, okay, plus temperature difference between T5 minus T6 is more greater than T3 minus T prime 4, right? T prime 4 is over there, right? So to further explain, assuming the gas is reheated to a temperature equal to T3, so differentiation of the expression of the specific work output shows that the optimum point in the expansion at which to reheat is when the pressure ratio and hence temperature drop and heat transfer for the high pressure and low pressure turbines are equal. Okay, and with this optimum division, it is then possible to derive expression for the specific output and efficiency in terms of the pressure ratio and the temperature ratio. Okay, so now we rewrite or writing back the methodology. Okay, they become as this. So where we introduce small c, okay, as the pressure ratio to the power of specific heat minus 1 divided by specific heat ratio. Okay, so this is the another expression. You can put back all of this inside, but to make life easy, okay, we just rename it as small c. Okay, this is equation 2.4, and we rearrange that to get this equation 2.5. Okay, because W specific work output divided by the specific heat capacity times the T1, which is equal to zeta, which is the efficiency. And this particular figure, figure 2.5, which is the reheat cycle, indicates that this is achieved at the expense of efficiency. So you can see that the efficiency can also drop, right, by having a reheat cycle if you have a temperature ratio at value of 2. At a high pressure ratio, you thought that yes, we are going to get a high efficiency, but not. The efficiency is about 40% or 60% the most if you have a reheat cycle. Comparison of the efficiency curve in figure 2.6 with those in figure 2.2b, later you can refer back at figure 2.2b, shows that reheat mark increases the specific output as denoted in here. And this is specific work output, okay, compared to, against the pressure ratio at different temperature ratio. Right, the last one for this particular session is on cycle with reheat and heat exchange. So number 3 just now, 2.13, only heat exchange. Then we look at only reheat. Now we combine. What will happen if we combine a cycle with reheat and heat exchange? Right, the reduction in efficiency due to reheat. Okay, remember the reheat maximum efficiency is about 40 to 60%, can be overcome by adding heat exchange. So we put back heat exchanger, okay, in the system, where over here we have, just after the compressor, we introduce a heat exchanger. Before it is, we have the combustion chamber, and we have the turbine, we have another combustion chamber, and we have the power turbine. So, and it goes back into the cycle. Okay, in terms of the TF diagram, it looks like this: 1, 2, 3, 4, 5, 6, 7, and then we have the station number 8, and the temperature is nearly at um, the ambient temperature, but it's slightly high because the heat exchanger that is not 100% efficient. Right, the higher exhaust gas temperature is now fully utilized in the heat exchanger, and the increase in work output is no longer offset by the increase in heat supply. Okay, it's because we have the heat exchanger, at the same time we also have the reheat system, right? So when a heat exchanger is employed, the efficiency is higher with reheat than without, as shown in comparison in figure 2.8 and 2.4. Okay, and the family of constant temperature ratio line exhibit the same features as those for the simple cycle with heat exchange. Okay, so now we look at the efficiency of reheat cycle with heat exchange. It is slightly different now. Okay, and each curve, right? So this one, the dotted line, is just reheat cycle. The solid line are representing reheat cycle with heat exchange. And the Carnot value of pressure ratio equal to 1, and falling with increasing pressure ratio to meet the corresponding efficiency curve of the reheat cycle without heat exchange at the value of pressure ratio corresponding to the maximum specific work output W. Right? Okay, so that's all for the first part of our lecture, right? So, as I said, it's only 40 to 50 minutes. Okay. Any questions so far from all of you?
Assalamualaikum, Doctor.
Salam, Syakir. Yes.
I have a question about the heat exchanger cycle.
Yep.
How is possible the ideal heat exchange T5 is equal to T4? Because after the process of exchange, it goes to process of combustion chamber, then turbine. After that, we get the T4. But for our ideal, how is it the T5 is equal to T4?
Can you repeat your question just now?
The question is about the after the airflow through the heat exchange.
Okay.
We got the T5,
Yep.
but state that with ideal heat exchange, T5 is equal to T4. But after the T5, we have the combustion chamber and then turbine. Then we got the T4. The
Oh,
temperature
okay,
is
with
same.
ideal heat exchange,
Ah,
T5 equal to T4, right? T5 here
mm,
equal to T4. Okay. This is due to the okay, the here over here when the air being compressed, right? What happened to the air actually? The temperature of the air increases, right? So again, this is ideal heat exchange, meaning that we assume that it is perfect. It is perfect where when the air coming into the combustion chamber is already being prepped to a very high temperature, and ideally we want it to be very high so that the combustion chamber doesn't work so hard. So and T5 is assumed to be T4. Of course, in the real case, it is not. So at the same time, when the T4, when the cycle continues, T4, okay, it goes here where we want to cool down the temperature, cool down the T4 to ambient temperature. We again assume ideal heat exchange where the T4 temperature is being reduced to T6, but at the same time on the cold side, T5 equal to T4. You get my point, eh? So that's the, because if you just reach at the beginning, it is not that high. T5 is not that high. Let's say you want to start the engine, right? At the beginning, from let's say 300 Kelvin goes into the system. Of course, even though it is being compressed, it's not that high. is not probably about 350 Kelvin before it goes to combustion chamber, and then it's already raised up to 600 Kelvin, for example. Okay? When it's being expanded, it's already reduced. Okay, T3, of course, T4 is less than T3. Okay, when the T4, let's say, is around 400 or 400 degrees Kelvin, when it goes to the heat exchanger again, the assuming ideal heat exchange, the drop of the temperature from T4 to T6, it is equal to the increase of the temperature of T5 to T4. Okay, the amount of heat being exchanged inside here. Okay, so there's a Q there. Okay, so that is what we assume. It is not in happening 100% in real case. Okay, it is an assumption that the heat exchanger is ideal. All right, so I hope it explained to you clearly. Probably you can listen back to the explanation earlier. Okay, when we have when you look into the recorded video.